of sums. So let's introduce the concept of remainder. So what we care about is this. Summation n goes from 1 to infinity, which means this formal sum. A1 plus A2 plus ... right? Okay. Now consider this. A1 plus A2 plus A3 plus ... up to a term, say an. And then you're supposed to continue to add an plus 1 plus an plus 2 plus ... Is that right? Okay. So how do you call this one? What's the notation we use? Partial sum. What's that called? Sn. Okay? And then what is the rest? That's called the remainder. Okay? So what I'm saying is that is, i.e., if summation n from 1 to infinity an is equal to, let's call it S. That's a sum. You know, it actually converges to S. The sum converges to S. Then remainder is defined as, you know, how much more after the nth partial sum, right? In order to arrive at S. So this is, i.e., S, the final sum is indeed equal to the partial sum plus something, and that something is called the nth remainder. Okay, so that's just introduce one more notation, capital Rn, and then the estimate of sum says the following. Okay, there. So, f is continuous eventually decreasing and positive. Eventually positive. Eventually decreasing. In other words, the same kind of conditions that you used in the integral test. All right, so in other words, you have a setting in which you're ready to use the integral test. And then you use it, it actually works. All right? And let's say 1 to infinity or a to infinity. Let's say 1 to infinity, then make things simple. 1 to infinity, f of x, you know what? If you don't mind, scratch this one eventually, because the reason that I scratch this is because here we really want to get the, some sort of numerical estimate, and therefore the part of f I want to use would be exactly the part which I'm sure that it is positive and then decreasing. Okay? And that is the part that I really want to use. So I might as well make things simple. I just assume that it's the nicest case possible is actually honestly, decreasing and positive all the way through. Then if I have this integral, dx converges. Okay? So summation f, and then third thing is still a condition that an is equal to f of n. So summation 1 to infinity an converges by the integral test. Okay, so this is a setting. I have a function which right from the beginning is positive and decreasing all the way through, continuous function, such that the improper integral converges. Right, so it's a very nice case, and therefore, if I define an at f of n, then this fits into the framework integral test because the improper integral converges, and therefore immediately conclude that the series converges. Right? Okay, so this is that setting. Then what I'm trying to say, the theorem says, then I care about Rn. Then I'm going to bound it. I assure you that I can narrow it down to a certain window. Both of them are integrals. On the upper end, I have n to infinity f of x dx. On the lower end, I have n to infinity n plus 1 to infinity f of x dx. So I'm claiming that it is sandwiched between the two. So here's a proof in silence. All right. So I'm not going to provide a very formal proof. The essence of the proof is encapsulated in the following picture, very clearly. So here's a picture in silence. Okay. So here's a graph of the function. Positive, decreasing. All right? And then somewhere you see n. Yeah? Okay. Then, as a matter of fact, I have to, if you're taking notes, copy the same, you don't have to erase. I just realized that I have to do it twice. So I should draw the same thing twice. Same curve. Okay. Here's n, same place. So I'm gonna draw two staircases. So the first staircase is this. I want to show that this remainder dominates a certain integral. Okay? So that's easy to establish. And that is because what is this one? This one would be what? An plus 1. This is what is left, after you have summed the first n terms. So the remainder therefore is the n plus 1 term plus n plus 2 term plus dot dot dot. All right? Okay. So the first thing that I'm going to do is this. The an plus 1 is which height? Isn't that this height? Okay. I'm going to turn this way. Yeah? And so I have a rectangle, width 1, this height. Then I consider this lower point and this lower point, etc., etc. Then I'm going to start here and build a staircase. Go down a little bit, go to the right and hit this point. Go down again, go to the right and hit this point. So it's a staircase. Is that right? And I'm actually proving the other half. So this piece over here is what? An plus 1. Is that right? What is this piece? An plus 2. And so altogether, I'm talking about this staircase. Would you agree that this staircase is dominated by which shaded region? Would you agree that it's dominated by what?
The region.
This one? And wouldn't that be this guy here? Alright? Okay. How about the other half of the inequalities? Well, I'm going to present that Rn differently. So once again, this height is sorry, this is An. So this height is An plus 1, right? But this time, rather than turning this way, I'm going to turn the other way. So this, from here, this is the first rectangle. What is the height? An plus 1, the first turn over there. But I presented it as this rectangle. Then you go down, hit this one, right? And then you turn to the right, and then go down to hit this one. So you have a staircase. Would you agree that that staircase dominates a certain shaded area, this shaded area? Is that right? So that staircase, once again, is the representation of An plus 1 plus An plus 2, and so on. So that's once again is remainder. So that remainder presented this way in this new staircase now dominates another shaded area. And that shaded area is smaller than this shaded area. Start from where? N plus 1? All right? And that is the stuff. All right? So, what this is useful is this. Suppose I give you a P series. Right? I give you a P series and say P equal to 2. Then I know that that P series converges. Then I want to sum the first, 20 terms. So I carefully calculate the first 20 terms I sum, I get a numerical value. And this is reasonably good approximation to the real sum, right? But not exactly equal to the real sum. So you are short of the real sum by a remainder. And then what is that remainder? Well, that remainder, I can give you a size estimate of that. If that remainder is at least as big as this, it's not as big as that one. So I give you a little window. Is that right? So because this one you can calculate, that one you can calculate. If you are dealing with a P series, for example, the f, the function actually is something that you can take antiderivative of, and therefore you actually can calculate this in proper integral as well as that in proper integral. So you get a numerical value here and here, and therefore you get an estimate of the remainder. All right, so not only once you sum up to the 20 terms, not only do you get an estimate itself, but also I've provided a bound, as estimate of size of the remainder. And therefore I know that, for example, if this remainder is somewhere between 0.01 and 0.001 and 0.002, I'm just hypothetically, right? Then that means that if the first 20 term is 3.